All right, so in part C, I just wanted to do an add-on here. In part C, we did this using discs and washers, and I did mention when I did it that this particular problem, because when we're going sideways here, here, let me draw that again. When we're going around a vertical line, like the y-axis, our discs and washers, you know, they go that way, right? So it's all dy. Because our boundaries change then, in other words, we have above the line, above this horizontal line y equals 2, we have this function and this function as our boundaries of the region. But below the line y equals 2, we have this function still, which was the y equals g of x, you know, y equals x. But now we have just x equals 0. We're not using the square root curve anymore. So because we have different boundaries, we had to do two separate integrals. And it got a little messy. I'll show you that work again here. This is what we did. And we kind of scroll down so you can see that answer again. We went through all that arithmetic, and at the end we didn't even simplify because it's kind of ugly. It does simplify down though to, I think, 224 over 15 times pi, if you put all this together with a common denominator. All right, what we're going to do now is the same stuff, but note all this work, right? If you see that, maybe you went through it with me in the video. And now you just see how choosing the right method for the right problem can make it much simpler. And you know, if you're curious about how cylindrical shells work, they're not in the AP curriculum, excuse me. They're neither in AB or BC. But they are in Calc 2 classes often. So if you take Calc 2 at a college, you may need to use cylindrical shells, or if an advanced calculus class, you may need to. So it's not a bad thing to have seen either. We actually don't need to worry about this boundary now, because cylindrical shells, it actually orients the other way. So when you're revolving about a vertical axis, like the y-axis, or if we had x equals -3 or something like that. You know, with discs and washers, you go sideways, but with cylindrical shells, what you do is you take, you know, a vertical rectangle for the ith subinterval, and we make, here I'm going to draw it closer to the left edge of this actually, so you can see it on the board. We make a cylindrical shell. So we revolve this whole rectangle around this way, so it looks different than the discs and the washers. Instead, it's like an empty soup can. Like a, you know, if you picture like a Campbell's soup can. They are not a sponsor of my videos, by the way. This is just, they're getting free advertisement. Maybe they'll sue with cease and desist because of how bad these videos are. I don't know. Anyway, we're going to take this rectangle and revolve it that way around, and it makes like this hollowed out can, like the sides of a can, like a tube, a cylindrical shell. It's a cylinder, just the outer shell of it. And if we do that all the way through, these shells just fit together and form the full solid. So if we do this one next, you know, and then you'll fill out the solid that way. It's just a different way of constructing it. So what we need to do is take the ith subinterval, the ith rectangle, and we need to picture that shell and how we're going to get the volume of that shell. So if you want the, really like the lateral surface area of a cylinder, right, like the vertical can part, right, then if you picture like doing surface area of a cylinder back in, you know, geometry and algebra classes, what you've probably thought about is like unwrapping the can, like either if you picture it as like metal and unwrapping it, or even like a label, like the Campbell's soup label going around the can, and peel it off the can and lay it out. It makes a rectangle. And the top of that rectangle, or bottom of it, the base of it, is the circumference, the distance around that circle, and the height is still the height. So that area of that shell, just around the outside, we're not including the circles at the bottom or top here. The area around the outside of that shell, that label, is just 2 pi r for the circumference times h for the height, because it's base times height of that rectangle. Okay? And then what we're going to do is we're taking that area, but we don't just want the paper label, right? We want like the soup can. We want that infinitesimal thickness there, right? Like that really thin metal thickness, right? That's the width of this rectangle for the ith subinterval, which is, that width is dx. So we're going to multiply, that 2 pi r to get this area times that infinitesimal width of dx. Of course, that's just built into the integral. And then that's going to give us our volume. And when you integrate, it adds them all up for you. So the question is, what are these things? The 2 pi is a constant. What are the r and the h that give us the, the r is part of the circumference and the h obviously is the height there. So let's take a look at that. Let me clean this up a little bit. And I don't have this one set up on Desmos to show, but I'll have to make that. I liked as a start, the diagrams I was doing for some of the other solids. So I'm going to keep working on that to make a good demo tool. Anyway, the height of this can, let's start there. The height of that is this right here. It's the difference between those two curves again, but this time again, the y values, right? It's a vertical distance, so it's y as a function of x. And again, that top curve was the f of x equals radical x plus 2. And the bottom curve was g of x. Oops, I don't want to write it there. It's in the way of what I'm about to write. The bottom curve was g of x equals x, y equals x, right? And so it's the top minus the bottom. It's radical x plus 2 minus x. That's the height of the can. That's h. Okay? And then the radius of the can is the distance from the axis of revolution, wherever we are. So when we're plugging in an x value to find that height, we're plugging it into these functions, and it gives us the height there. But the radius is just the distance from here to the axis of revolution. And since here the axis of revolution is just the y-axis, it's just x equals 0, then it's going to be this x value, which is just x, minus 0. So it's just x. The radius is x. Now, if we were going about a different axis, like x equals -1, for example, then it would be x minus -1 for the radius. It'd be plus 1, x plus 1. So that's our basic idea for our setup. So let's go ahead and put it together. That cross-sectional, well, it's not so much a cross-sectional area now that we're using. This cylinder area, the 2 pi RH, is going to be 2 pi times r, which again, r is just x, and then times h. Again, h is the top curve, radical x plus 2 minus the bottom curve, which is just x in this case. That's the g of x curve. And for notation, in case you're trying to generalize this was our f of x, and this was our minus g of x. Top curve minus bottom curve is where those came from. Okay? This is just x because it's the distance from the x value of the ith subinterval, wherever you are, to the axis of revolution, which in this case is 0, x equals 0. So it's x minus the axis, or the axis minus x if we are to the left of it, which again, I might hit that in another video. So yeah, that's the setup there, all right? And we want to integrate, right? We're going to integrate this whole area times dx, and the 2 pi is just a constant, so it doesn't have to be in the integral. It can be factored out like that. And we're just going to go from the left endpoint of this region, 0, to the right endpoint, which is 4. So 0 to 4. And this ends up being much nicer in terms of the arithmetic than when we did this one with shells and discs. Or sorry, with washers and discs. We're doing shells. It's nicer because, mainly because we don't have to break it into two integrals and then have plugging in 0 and 2 and then 2 and 4 into the two different sets of things. This is just, it's going to be cleaner. Stuff's going to cancel out kind of quicker and easier for us. So it's not that shells is always better, it's that for this problem, shells is actually better because of the way that we're going with the revolution and how many regions we need, or how many intervals we need, I guess. We just have one interval, 0 to 4, because it's the same boundaries the whole way when it's shells for us. All right, so anyhow, sorry. Equals 2 pi, this is our volume, okay, times the integral from 0 to 4. We're going to distribute first, right? That's how you do this integral. So we're going to have x to the 3/2 plus 2x minus x squared. We still haven't actually done the integration yet, the antiderivative. So we'll do that now. 2 pi, and then we're going to have x to the 5/2 times 2/5. And then plus x squared over 2 times the 2 is just going to be x squared, and then minus 1/3 x cubed. And this goes from 0 to 4. So we'll go a little further here. And now when we plug in the 4, when you do the square root before you do the 5th power. It's easier. You'll get 2. 2 to the 5th is 32. So we get 32 times 2 over 5, so it's 64 over 5. Otherwise, you'd have had to do 4 to the 5th is 1,024 and done the square root of that and known that that was 32. All right, plus 4 squared is 16, and then minus, and it's going to be 64 over 3, because 4 cubed is 64. And then when you plug in 0, it's just 0 for all of them. And so that's it. We've done it. And if you evaluate this out, it comes out just like part C, the first one I did, does. If you put it all together, it should come out to 224 pi over 15. Again, with something like this, if you're not using a calculator, I think an answer like this is probably fine. We've done the important parts. But yeah, this is it. And that's with the cylindrical shells.